All right, let's dive in. Today, we're going to tackle one of the most beautiful, honestly, and fundamental areas of math, topology. And we're going to use a classic text, Marsden and Hoffman's Elementary Classical Analysis, specifically Chapter 2, as our guide. This is where we get the real nitty-gritty language that mathematicians use to pin down ideas like nearness, continuity, and limits. Ready? Let's get started.
So here's the plan. First, we'll ask, what does nearness even mean, mathematically speaking? Then, we'll get into the big one, the open set. Seriously, everything builds from there. Once we've got that, we'll see how it lets us define closed sets, boundaries, some really important types of points, and finally, where a sequence of points is actually going. It all just clicks into place, one step at a time.
All right, section 1, let's jump right in. The very first hurdle in topology is taking something that feels totally obvious, like points being close to each other, and making it rock solid. Because, close is kind of slippery, right? How do we nail that down with mathematical precision? I mean, really think about it. You can't write a proof and just say, well, these points are kind of close. It just doesn't work. You need a real tool, a precise definition that leaves zero room for doubt, and works whether you're on a line, in a plane, or in some crazy high-dimensional space. So, what does that tool actually look like? Well, it looks like this. This little thing is the epsilon disk, or epsilon disk, and it's the simple, absolutely brilliant answer to our question. It's so easy. You pick a point, you choose some tiny distance, we'll call it epsilon, and you just draw a little bubble around it. Could be a circle, a sphere, or just an interval on a line. And voila, everything inside that disk is now officially, mathematically, close to your point. This is it. This is our fundamental building block.
Okay, so we've got our building block. Now, let's see how we can use it to construct what is, and I'm not exaggerating here, probably the most important idea in all of topology, the open set. Seriously, if you can wrap your head around this one concept, the rest of the stuff is going to fall into place so much more easily. So here's the formal definition. A set is open if every single point inside it has a little bit of breathing room. What that means is no matter which point you pick, any point at all, you can always draw a tiny epsilon disk around it that's still entirely inside the set. It never pokes out. Basically, an open set is a set that doesn't include its own edge. And this picture? Perfect illustration. Just look at the shape. Go ahead, pick any point inside, anywhere you want, see? You can always draw a little circle around it that stays completely inside the shape. Now, you might be thinking, what about a point really close to the edge? Well, you can still do it. You just have to make your circle, your epsilon, smaller and smaller. That's what makes this a classic open set. Okay, now let's look at the opposite. This set right here is not open. Why not? Well, it's all because of points like this one, x, sitting right on the boundary. If you try to draw an epsilon disk around x, doesn't matter how tiny you make it, part of that disk is always going to be outside the set. Uh-oh, it fails the test. So that's the key takeaway. If a set includes its own boundary, it's not open, period. So open sets have some, let's call them, rules of the road for how you can mix and match them. It's pretty interesting. If you take the overlap, the intersection, of a finite number of open sets, the result is always open. But for unions, where you just kind of lump them all together, you can take an infinite number of them, and the result is still open. Now, that difference between finite and infinite, that's not just some random detail. It's absolutely crucial. Why? Because if you could intersect an infinite number of open sets, you could shrink them down to a single point, and a single point is definitely not open. These rules are basically the bedrock of what we call a topological space. Okay, so hopefully open set is starting to feel pretty solid. And what's so cool is that now, with just this one idea, we can define the entire rest of the landscape. We can finally talk about what a closed set is, and what a boundary is, with total precision. Let's put them side by side. An open set, as we said, contains none of its boundary points. It's like a field without a fence. A closed set contains all of its boundary points, the fences included. But there's an even cooler, more elegant way to define closed. A set is closed if everything outside of it is open. Think about that. You define something by what it's not. And this seemingly backward definition is actually a secret weapon when you're doing proofs. And this naturally leads to the idea of the interior of a set. It's actually a pretty simple concept. The interior is just the biggest possible open set you can fit inside any given set. Imagine you have a slice of bread with crusts. The interior is like
cutting off all the crusts, leaving only the soft, open part in the middle. You're just getting rid of the boundary and keeping all the points that have that nice breathing room.
This visual really nails what a closed set looks like. See? It doesn't matter if it's a solid shape or just a line. The key thing to notice is that the boundary, the line itself, is considered part of the set. Those points are included. And that's exactly why these sets are not open. The boundary is like the ultimate dividing line, right? It separates what's inside from what's outside.
All right, let's switch gears a little. We've been looking at whole sets, but now we're going to zoom in and focus on specific kinds of points that have special properties. And this next one, the accumulation point, oh man, this is absolutely essential if you want to understand things like limits and derivatives in calculus.
Okay, so here's the official definition from the book. A point X is an accumulation point if, for every epsilon disk you draw around it, I mean, no matter how ridiculously impossibly small, you're guaranteed to find at least one other point from your set in there. It's a point that is never, ever truly isolated from the rest of the set.
So what does that actually mean? Let's break it down. Just think of it as a cluster point or gathering point. It's a spot where points from the set just pile up. They get infinitely, arbitrarily close. And here's the mind-bending part. The accumulation point doesn't even have to be in the set. The classic example is the best. Think about the set 1, 1, 1/2, 1/3, 1/4. Where are those numbers headed? They're all clustering around 0, right? So 0 is the accumulation point, even though 0 itself isn't in that set. This right here, this is the topological soul of the concept of a limit. You know, this whole idea of getting arbitrarily close is the perfect bridge to our final topic, sequences. This is where we stop looking at static pictures of sets and start thinking about motion, about a journey of points. And topology gives us the tools to ask a really fundamental question about that journey. So, what's a sequence? It's really just an infinite ordered list of points, a journey. And the big question topology helps us answer is simply, where is this sequence going? Is it actually heading toward a specific destination? Or in math terms, does it converge to a limit? The formal definition of convergence can be a little dry, so let's turn it into a game. It's you versus me. Your move is to challenge me with a tiny target distance, some positive epsilon, anyone you want, as small as you can imagine. My job is to respond by finding a point somewhere down the line in the sequence, we'll call it the nth term, such that every single point after that is within your target distance of the limit. If I can always win this game, no matter how tiny an epsilon you throw at me, then boom, the sequence converges. And really, as Marsden and Hoffman point out, this probably isn't a brand new idea for you. If you've ever touched calculus, you've seen this before. It's just the intuitive feeling that, eventually, the points in a sequence get super duper close to the limit. And then they just stay there. All topology does is give us the ironclad, absolutely precise language to actually prove it. So think about the journey we just took. We started with a simple little bubble, the epsilon disk, and from that one idea, we built up a way to talk about nearness, open sets, limits, and finally, the convergence of sequences. We've basically assembled the foundational toolkit for so much of modern mathematics. Now that we have this incredibly powerful and precise language, what else can we build with it? That's the really exciting question. Thanks for diving into this with me.